if I have two objects that are moving at the same velocity, but one's more massive, well, the more massive object is going to do more damage when it hits the wall than the less massive object. And the amount of damage done turns out to be a pretty good way of thinking about how much kinetic energy something is carrying, right? The more kinetic energy it's got, the more likely it's going to put a hole in the wall, right? And a bigger hole gives more kinetic energy. So it makes sense. Notice that it goes like the square of velocity. So not only is it the case that it's always positive, but it's a pretty strong function. It's squared with velocity, right? So if I double how quickly this thing's moving, right, that results in 4 times the kinetic energy. As opposed to doubling its mass, that only doubles its kinetic energy. It kind of makes sense that doubling the mass doubles kinetic energy, right? If I have two pieces of chalk at the same mass and I throw them both at the same speed, it makes sense that whoever gets, well, no, I wouldn't do it in a person, but whoever it bumps, right, is going to receive twice as much energy. It's going to be impacted twice as much as if I just threw one of the two things. But velocity, if you double the speed, it doesn't double, it quadruples the amount, right? All right, so good. That's the definition for kinetic energy. As I said, there's multiple kinds of potential energy possible. Gravity is the simplest one because it's just a linear function of how high you are, just mgh or mg delta h. Once you choose your 0 point for h, you can just say, okay, in this problem it's just mgh. But already that would remind us that it's arbitrary where you choose your starting point. So what about springs? One more thing I should do, which is units. So I've introduced this new concept of energy. What are the units of energy? Let's talk about that real quick. Well, this equation tells us, oh, I'm sorry, this is work. So it turns out work and kinetic energy and potential energy, all these things, right, have the same units, right? It's all the same units as force times distance. And then here you say, wait a minute, that's mass. Well, let's check it's the same, mass times velocity squared. So the units of work, right, what are those? Well, it's force, so it's newtons times newton meters. And sometimes I'll write it that way, newton meters. There's a name for that, which is a joule, right, capital J. But we can also write it in terms of seconds and meters and the rest of it, right? So another way to write that is, let's see, a newton is a kilogram meter per second squared times meter. So the kilograms meter squared per second squared. So all those are the same. I don't care which way you like to write it on your exams or whatever else. Mastering physics might care, so be careful how you enter stuff. Actually, one thing about mastering physics I don't like is that often you're not asked to enter units. Usually what it does is it has the units written on the side and then you enter a number in a box to 17 decimal places or something, right? So, with omegas and everything else. So, but just it's good to keep track of what units are and remember. There's lots of different kinds of units for energy, partly because it's taxed in every country in the world, right? So every country has their own language and they have their own history. So there's all lots of different units for even among English-speaking countries, right? Like there's the BTU, the British thermal unit, and there's calories. There's calories in food and there's calories. It turns out that on food, you probably all know this, but on food containers it says calories. Those are really kilocalories, right? They left that 1,000 part off to make you feel better about how much they were eating, But it's actually kilocalories as compared to the kind of calories we talk about in the physics class. Now in this class, I'm always going to be using joules. Another unit you're used to though on your heat bill is kilowatt hours, which is a pretty strange unit. Kilowatt is actually a measure of power, so we'll talk about it in a little bit. That's energy per time, and then you multiply it by hours, so it's actually an energy unit, but it's a weird one. Anyway, so what we'll usually use those joules, newton meters, otherwise known as kilogram meter squared per second squared. Great. So let's check. Oh, and that was for work. Let's check to make sure that kinetic energy has the same units, and it does, right? Because it's going to be meters, that's kilograms, and then we got v squared, so that's meter per second all squared. That's meter per second. Good, same. Has to be the same units. So good. Great. All right. So given all that, what about springs? How much potential energy is there in a spring? So I've got a spring here, and there's one complication which I'm going to ignore for the moment, and I'll talk about it in a little bit, which is the fact that right now there's two forces acting on this block. There's gravity and there's a spring. Let's forget gravity for the moment. Let's just think about a spring. So suppose I got a spring. Imagine this is on its side, right? Or we're doing this in outer space or something. Right? So if what I do is I extend this guy by some amount, I'm actually storing up some energy in the spring, right? So if I let go, it's going to spring back, and it's going to speed this guy up and give it some kinetic energy. So it's actually storing energy to do this, but it's also storing energy to compress the spring, right? If I let go, it also moves. The only place where I can let go and it doesn't move is at the equilibrium position of the spring, right? That's where the spring is exerting. Well, all right. If it's on its side, it's exerting no net force. Let's do include gravity right now and just think through what's going on there. So if I make a free body diagram of this weight, right, hanging on the spring. Well, here's the situation. I got a spring that's doing this, and here's my weight. It's got some mass m. Here's the ceiling, right? And I can say, all right, well, the free body diagram says there are two forces acting. There's the spring force, the force of spring, and then there's mg. If it's not, force of gravity. If it's just holding still like it is right now, so there's no acceleration. I know by F equals ma, F net equals ma. The net force is zero. So these are equal and opposite, right? So it's true that right now the spring is displaced by an amount, right? That winds up essentially giving it a new. So there's two ways to think about it. One is to say that here's the equilibrium position. There's two forces acting on the weight, the downward force of gravity and upward force of the spring that cancel out. The second way to think about it is, well, once I've established this new position, it's essentially an equilibrium position for the situation. I can stop talking about the force of gravity and just say, okay, let's just lump that force of gravity into the force in the spring and say there's this total force that's due to the spring and gravity, and that right now is zero. And if I extend this a little bit, now there's an upward force due to that combined gravity and spring. And if I raise it a little bit, now there's a downward net force due to the spring and gravity. Either way you want to think about it is okay as long as you label things carefully. But how much potential energy is being stored by our definition in a spring when we displace it by some delta x, right? So springs are one-dimensional objects. Well, not always, but for this kind of spring, that's true. So let's do it this way. Let's have the wall over here and say, all right, I've got some spring. I've got my weight on the end. Doesn't even matter what the mass is. When we calculate the potential energy, it's not going to matter what the mass of this object is, but I'll just call it anyway. And there's some displacement. So let's say that this is its equilibrium position. This is where it wants to sit when the spring is exerting no force. So we'll call this x equals 0, or if you like, delta x equals 0. You can say that. And then we displace it. So now we've got some non-zero delta x, right? And the spring is stretched out. So first of all, which way is the force being exerted on this mass now? To the right or left? To the left. It's a restorative force going that way, and it's proportional to the displacement. Remember Hooke's law, right? Hooke's law says force of spring equals, and I'll just do it in the x direction, right? So it goes in the negative direction of some spring constant k, some positive constant, which is big for a stiff spring, it's small for a floppy spring, a slinky or something, and then we have delta x, right? So that's all I mean by that's Hooke's law. So now let's plug that into our definition of work and see how much, or our definition of potential energy, how much potential energy is being stored. So if you say, all right, the potential energy then is stored up in the spring, and you displace it, is equal to negative, and let's go from delta x equals 0 to some new x value, and we'll just call it x. So we're going from the equilibrium position, this is important, it's the equilibrium position. So for springs, there is a special position in space, right? Then we do this. You say, all right, and then we're going to put in, what's our definition say? We need force on the object. That's why I've got a minus sign here. Oh, excuse me, no, this is a different minus sign. So this minus sign is coming about because of that equation right there. The force on the object itself, right, is negative k x, and now I need a dx out here. All right, so there's two minus signs that appeared in this equation. One minus sign came about because our definition for potential energy is that the force on the object due to this force, in this case a spring, the work due to that is going to be negative potential energy, so we get one of those. We get a second negative sign here because the force from a spring is always opposing the displacement. So these cancel out, and we get a positive number out. And what do we get? We get, let's see, so what's the integral of x? That's what I can do. X squared over 2. Right? So I get 1/2 k, because the number comes out, times x squared. And I evaluate it at x, and then subtract, we evaluate it 0. Well, 0 squared is 0, so I'm about to write the term that, you get this constant integration, right? It's 0 in this case. So here's my answer. Now notice that this depends on x squared, not x. And that means, just like the kinetic energy, it doesn't matter what the direction of x is, you get a positive potential energy. It's not like gravity. So for gravity, if I go up, I'm always increasing my potential energy due to gravity. Whereas if I go down, I'm always decreasing the potential energy due to gravity, right? But with a spring, if I start at the equilibrium position, if I go up, I've increased my potential energy due to the spring. And if I go down, I've increased the potential energy due to the spring. Why is that? Because in both cases, I was opposing a force from the spring. In both cases, I'm storing up energy because I'm doing positive. In other words, I'm doing positive work on the spring to stretch it, so it's doing negative work on me, and I'm doing positive work on the spring to contract it, so it's doing negative work on me. So if you start, so the equilibrium position is the lowest potential energy position there is for a spring. It's got a minimum. Unlike gravity, where you can keep going lower and lower and lower as long as you don't run into something, right? You hit the ground eventually. But if you dug a big well right here, if I put the chalk down, it would continue to decrease in potential energy due to gravity the deeper it goes. And likewise, if I shoot up into space, it would continually increase the potential energy due to gravity, on and on and on and on. Now, of course, if it gets turned up from the Earth, then the force of gravity diminishes and it becomes a tiny little increase. But nonetheless, it will keep increasing. So this is different than gravity in that it goes like x squared, not like linear in h over there. This is always going to be a positive quantity if we choose the 0 point as we did here. We chose the 0 point for our potential energy to be at the equilibrium position. And so it has some of the same properties as gravity, some different properties. And this will be really helpful for us. All this will be really helpful. The reason I'm bragging about potential energy and everything is it's going to wind up making problems easy to solve. When we need to calculate kinetic energy at the end of the day. So let's see. What order should I tell you these things in? There's a lot of things to say about all this stuff. So I'm going to tell you about the work energy theorem, and that'll make it clear why I think it's important to know about these things. So the work energy theorem just tells us, here's the work energy theorem. This is a sort of a pint-sized version of the conservation of energy we're going to be talking about much more on Thursday's lecture. The work energy theorem says that the change in the kinetic energy of something is just the network that was performed on it. And I'm going to write here on the object. So this is some particular object has some kinetic energy. It's changed by some amount. How much? Well, by the network that was on it. So before when we talked about the chalk, and I said, oh yeah, I'll raise the chalk up. Well, I did positive work on the chalk. Gravity did negative work on the chalk, but by the same amount that I did. And if the chalk didn't accelerate the whole time, it was moving at constant speed, right? Well, in fact, we use that fact to figure out that my force on the chalk is the same as gravity's force on the chalk, just opposite direction. So the network on the chalk is 0. That means the change in the kinetic energy of the chalk is 0 as a result of this. And sure enough, it's moving at some speed at the beginning, and at the end it's moving at the same speed. So 1/2 mv squared is the same at the beginning and at the end of the motion of the chalk. Why? Because the net work performed on the chalk was 0. I did positive work, gravity did negative work, but they canceled out. Net work equals 0. So why is this true? Well, let's write it out. So here, I'll do one derivation here. So net work, right? What is net work? It's the integral of the force, and what force? The net force times dx. We'll just do this in a one-dimensional. We'll just make this a one-dimensional problem. So we can calculate how much work is performed on the object, right? So the net force on the object times dx if it's a one-dimensional. So the force is equals it's some x component and then there's no y component. So it's all pointing in the x direction. No. So my parentheses and then parentheses. All right. Okay. So what can we say about that? Well, let's break it down. I did this in the book. I'm just copying their notes here. This is kind of useful for people to see too if you're not used to seeing different. If you haven't worked with differentials for a while, you don't really need to know it, but it just helps you understand where stuff comes from. So dv dt, this is just ma, right? F equals ma. So I use Newton's second law to get here. So Newton's second law implies that the network then equals this times dx. And what is this? Well, I can rearrange these terms, right? These differentials, as long as everything's well behaved and as long as all the functions here, as long as v is a function of time and x is a smooth function of differential and there's no weirdness going on, things are all well behaved, then I can swap these guys around. I can switch these two. They're just like numbers. And if I do that, then I wind up with the network equals integral of m. Let's see, it's dx dt times dv. All I did was I swapped the dx to the dv. And I was kind of coy about my limits of integration because now I'm going to change variables about what it is I'm integrating over. So okay, but there's some corresponding initial velocity and final velocity that goes along with the initial position and the final position. Yada yada. And when the escalator is what you get, well, this is just velocity, right? So this is the integral of mv dv. Well, we've done this integral 3 times today, so this is a linear integral. So what do you get? You get 1/2 mv squared. But now let's put our limits of integration in. Let's say we go from v initial to v final, right? So that means I'll get v final and I get 1/2 mv initial squared. So that explicitly shows you that the net work on some object actually does correspond to the change in its kinetic energy, because that's what this is. This is the final kinetic energy, 1/2 mv final squared, minus the initial kinetic energy, 1/2 mv initial squared, right? So the net work really is just the change in its kinetic energy. As I said, this is a pint-sized version of conservation of energy, because if we think about the work that's being applied to something in the context of, like, suppose the only force acting on this was a conservative force, one that's only going to depend on position, like gravity, then we can attribute it to a potential energy due to gravity. And we'd say, oh, well, then the net work, the work due to gravity in the case, like suppose I just drop this chalk, only force acting on is gravity. The net work that's performed on the chalk is just the work from gravity. That corresponds to a decrease in potential energy due to gravity, right? And an increase in kinetic energy. So one way to think about it is that the potential energy due to gravity plus the kinetic energy of the chalk, those things add up to a constant. They don't change. So we can define a conservation law. So that's the basis. This is a pint-sized version, a piece of the more general rule, which we're going to use a lot on Thursday about conservation of energy. So a lot of this is sort of getting what's coming up. But this is a basic point of where it comes from in terms of how you relate kinetic energy to the network on an object. All right. So lots of high-minded concepts at the board. Here, let me define one more thing, and then let's do some demos. Power. If you're like me, you care about power. So we're gonna. So, that's not true, really. But anyway, yeah. So I wouldn't have taken this job. But anyway, so power. What is power? Power is the change in the work per unit time, right? So, and what kind of power? Let's do instantaneous. Instantaneous power. Well, whenever it's instantaneous, means there's a derivative in there someplace. So it's going to be the change in the work with time, right? So if you're delivering power, right? If I'm providing positive power to some other thing, I'm doing positive work on it. And I'm doing and over some length of time. So if you want to know what's the average power? The time, in other words, the time average power. Time average power. What is that? Well, we often write that with a bar on top. You say, oh, what's that? Well, that's just the delta W over the delta T. Power, right? Easy. And this is pretty easy too, but anyway, you don't have to take care of this. So, all right. So what else do we need to know? Well, another way to write this, right? So one way to calculate. If I said, oh well, suppose I've got a certain amount of work. I moved this chalk 1 meter, right, from here to here. So first of all, was I doing positive power? Is that positive power from here or negative power if I raise the chalk from here to here? It's positive. If I went through 1 meter, say, oh well, I know how much work I did. I added 1 meter's mgh. So whatever the mass of the chalk is times 10 meters per second squared times 1 meter. Was it right there? Mgh. Yeah, you calculate that, and then you say, all right, how long did it take? Well, if I did this in 1 second, I divide by 1, and that's how much power I delivered. And what are the units of power? The units of power are joules per second, right? Because it's work per time. And we can write that out in terms of, oh, that's Newton meters per second. And we can write that out, again, as well, this is kilogram meter squared per second squared. So it's a kilogram meter squared per second to the third, if I'm not mistaken. Is that right? So it's just this proliferation of units, right? You get more and more stacking up. But that's okay. I usually think of it as joules per second. But if you need to make sure that you got the right units for something, that's what it is, right? Six different things. A kilogram, 2 meters, and 3 seconds. Anyway, great. So that's power. Oh yeah, I was going to rewrite this another way. So we can do some more mumbo jumbo like we did here to rearrange differentials and everything. And what happens? Well, you can think of dw dt as the dot product, because if you write the work out as the force dotted with the displacement, right? It's the dot product of the force and the velocity. Let's make sure this has the right units. So this is a Newton. This is meter per second. Yeah, Newton meter per second. That's right. So that's another way to think about power. It's the force dotted with the velocity. So what does that mean? It means that if you know how much power something is delivering, how much power gravity is delivering to this chalk, say, well, instantaneously, if you know its velocity, if the chalk is falling, right? Well, for one thing, so while the chalk is falling, is gravity delivering positive or negative power to the chalk? So which way is the force of gravity pointing? Up or down? Down. Which way is it moving? Up or down? Down. So this is positive or negative? Positive. Doesn't matter which way you got your x-axis or y-axis pointing, right? The sign of this is determined by the relative directions of these two vectors. So suppose you have the x-axis pointing upward in the falling case. You say, oh, that's negative mg, and this would be negative, whatever it is, 3 meters a second. Negative times negative, you get a positive answer. If you head downwards your positive direction, you get positive mg, you get positive velocity, you get positive 3 meters a second, so you still get positive. So the work being performed by gravity, the sign of it does not depend on your conventions for which way your axes are pointing. The change in the potential energy, the sign of it doesn't depend on your directions for your axes, or what you call x or y, or which way positive x is. But the change in the potential energy of your gravity does depend on where you choose to make the zero. Excuse me, the change does not. The absolute value, like the absolute, what you assign the potential energy to be at a given height, that is up to you. That's one thing that depends on your convention. Right? Okay, good. So power. So now I'm giving you the definitions from chapter 6, and I've tried to give you a lot of context, and we've even calculated the potential energy. Although there's one more thing I should do. For potential energy in a spring, did I actually write this out explicitly? The potential energy, I calculated it. Yeah, I sure did. One thing I should do is draw a picture, just to make it clear why. So in this case, it's easy to see where the half comes from. You say, oh, well, what's going on is, if I want to know what the potential energy for a spring is as a function of x, well, I know what the force is. Oh, excuse me. I meant to do this. I meant to say force of the spring. The force is linear with x, right? When I do an integral, I'm doing an area under the curve. So this is essentially what's going on. Here's the potential energy to the spring. It's the area under the curve. That's what I meant by potential energy to the spring. That's where the half comes from, right? Because this distance is x, and that's x, that's 0. Here's 0, because we chose this to be the equilibrium position. That means the force is 0 here, right? And the max force, or the value point along the way, is just equal to k times f. Oh yeah, this is supposed to be negative, yeah, but there's another minus sign in front, so those cancel out. So the area under the curve we're talking about is a triangle, right? With a slope given by this k. So it's k times f, the height times x. Excuse me. Let me say k times x. Let's get the right unit. So it's got k times x, that gives me kx squared, but only half of it, only the lower half triangle. That's where the half comes from. So it's 1/2 kx squared. All right. Super. Okay, enough of the blackboard, huh? So let's think a little bit about, I've given you all this sort of simple example, like, yeah, positive, 0. You know? Yeah. So let's do a more interesting example for work. That'll get us thinking about why it's useful to think about, why is there's no free lunch? You know, can I have a volunteer come up here? Who's trustworthy? Trustworthy? No one's trustworthy. Oh, come on up. Oh, thanks a lot for coming up and helping me here. That's a light applause. This is to encourage you not to drop me. So what you're going to do is hoist me up in the air with this thing. Here you go. Oh, I think there's gloves. Are gloves here? There are no gloves, but you won't need them. No, actually, no. Maybe I'll ask you to use your bare hands. But it shouldn't be, if it's too much, let me know. But I don't think oh, yeah, I know how to do this. I do this every year, and you think I remember how to do it by now. All right. This is a Bosun's chair. So we talked about ideal pulleys. These are not ideal pulleys, but they're close enough that our equations will be well within a factor of 2 correct. Okay, you got it? Can she hold me up with this? What do you think? So what do pulleys do? Pulleys are useful for redirecting the direction of force. That's how we've used them so far, right? We have the funny cart, and there's a string comes on side, there's a pulley, and there's a weight hanging, right? In those cases, though, there's a tension in the rope. And let's assume that these are ideal pulleys. They're not, but they're close enough that you can get away with it. So that means that the tension in this rope will be the same as on the other side. But what about, there's so many, why have 3 of them? What's the point of that? Does that do anything? You see these lots of pulleys on, I think these people are just, it's like a fetish. It's always pulleys. It doesn't seem like it's really going to make any difference. So all right, so here we go. I'm going to sit down, and I'm going to venture a guess that I weigh more than you. So if that, okay, can you